Hi, I'm Qianfan from Princeton University, and this is a video of our ITCS'25 paper, Bicriterion Concentration Inequality and Profit Inequalities for K-fold Matroid Unions. This is a joint work with Noga, Nick, Tristan, Aviad, Hongao, and Matt. Our paper consists of two parts. In the first part, we will show a Chernoff strength bicriterion concentration, which I will explain what this means very soon. In the second part, we will investigate nearly optimal profit inequalities, and we will show that first, large girths does not suffice for a nearly optimal profit inequality. On the other hand, any k-fold Matroid unions do suffice, and our proof is actually heavily relied on our bicriterion concentration inequality result in the first part. Let me first introduce our first result, which is a bicriterion concentration inequality. So as a computer scientist, we use concentration inequalities a lot in different settings. But for now, let's focus on this canonical scenario, where there are n independent Bernoulli random variables denoted by a vector of x. And we are further given a function f that maps every 0-1 vector to a real number. And the function we require to be both monotone and one Lipschitz. Note that we say f is monotone if f of x is smaller or equal than f of y, whenever vector x is smaller or equal than y element-wise. And we say f is one Lipschitz if flipping a single input bit changes its output by at most 1. Given this, the question would be, how well does the random variable f of x concentrate around its expected value mu? And specifically, we will be interested in its upper tail with some small deviation t. Note that when this function is exactly a sum over variables, then the Chernoff bound gives us a very good tail bound. Indeed, this implies a standard deviation of square root of expected value mu, as the bound can get arbitrarily small when the deviation is in the order of square root of mu. It turns out that such concentration inequality can be extended to several special class of one Lipschitz functions, such as monotone submodular functions. One example would be the Matroid rank functions. So for these functions, we can show that they all satisfy a property called self-bounding. Then, by applying the concentration inequalities for self-bounding functions, it will give us a Chernoff bound or Chernoff strength tail bound. And this bound also implies a standard deviation around the square root of mu, which is as good as Chernoff bound. On the other hand, for general one Lipschitz function, the best we can hope for is basically McDermott's inequality, which gives us the following bound. And this bound turns out to be much worse than the Chernoff bound, because it is dependent on the dimension n, and it implies a square root. The standard deviation is square root of n instead of square root of the expected value mu. As a result, this bound does not tell us much when mu is much smaller than the dimension. And the bad news is that, in general, it's impossible to get a Chernoff strength bound, because there exists one Lipschitz function f, such that f of x can have a very small expected value, but with a large deviation. Now, we're ready to introduce our bicriterion concentration, where we will introduce another parameter s that controls how much we want to scale down the original probabilities of x. Specifically, we will set each random variable xi to 0 with a small probability 1 minus e to the minus s, which is approximately s when s is small. And we will denote this new random variables x to the s. Our bicriterion concentration inequality says that for any scaling factor s in 0 to 1 and any deviation t, the probability of the scaled down f of x to the s exceeding the original expectation of f of x plus t is upper bounded by e to the minus st. Note that this bound is dimension-free, which is very important for our application later. Also, by setting parameter s and t correspondingly, we can obtain the following nice-looking Chernoff-Stranz tail bound. The only difference between this bound and the Chernoff bound is that we are now comparing the scaled-down version fx to the delta to its original expectation, e of f of x. And one of the intuition of why such a bound might be true is that for the function f of x at any specific point x, either the function changes fast, which means the scaling down really bites us a lot, or the function changes slow, but that will imply the original random variable f of x already concentrates somehow. And of course, these are very high level intuitions, and it turns out that they actually doesn't work out. These intuitions. Nevertheless, our proof is a unified analysis based on the entropy method with the following unconventional function that is not a moment generating function. So if you're familiar with all this line of work. Now, let's move to the second part of our work, which is profit inequalities for k-fold Matroid unions, which use our bicriterion concentration inequality. Let's get started with the classic single item profit inequalities. Say there are several treasure chests, and each contains an item with a value following a non-distribution. At each step, we're going to inspect the corresponding chest, and then we have to decide immediately and irrevocably whether to take the item or not. For now, let's consider the single item case, which means that one can accept at most one item. And for instance, let me inspect the first chest and get to see a value of 6, which I decide to reject. Then the second chest gives me a value of 1, and I also decide to reject it. The third chest gives me a value of 5. Because there's only one remaining unopened chest, I decide not to take the risk and just accept the item. And that will be the end of this process. The goal for us is to maximize the accepted value in expectation. And we want to match this value with a profits value who knows everything and always gets the maximum value. For example, it's possible that the last chest actually gives us a value of 8, which will then be profits value in this specific realization. And formally, for an online algorithm, we will say it's alpha competitive if the ratio between the expected value the algorithm gets and the expected profits value is at least alpha in the worst case. The classical single item profit inequality says that for any distributions, there exists a simple one-half competitive algorithm, which is to accept the first value that is greater than a fixed threshold t, defined as the median of the maximum value overall. Also, it turns out that this competitive ratio of 1/2 is tight in the worst case. A natural extension to the single item setting is to allow more general feasibility constraints. In this setting, we're further given a family of feasible sets, F, which is guaranteed to be downward closed. And during the whole process, we must keep the accepted item a feasible set. The goal now becomes to maximize the sum of accepted values. There are a lot of different results for various feasibility family. One of the seminal results by Kleinberg and Weinberg shows that a competitive ratio of 1/2 is still achievable whenever F is a matroid, which is a very common type of feasibility family. And note that this result is trivially tight because it is even tight in the single item case, and single item is a special matroid. On the other hand, Alon showed that a competitive ratio close to 1 is achievable for K uniform matroids with a large K, which is exactly the setting where one can accept at most K items. A natural follow-up question would be, what conditions on the feasibility family F suffice for a nearly optimal, which is 1 minus epsilon competitive profit inequality? And we want to answer that question. To answer this question, our plan is to find what makes K uniform matrix easy for profit inequality. For example, is it because of it has a large girth, or is it because of being a union of many matroids? Well, our first result is that having large girths alone does not suffice for a good profit inequality. Recall that for any feasibility family, the girth can be defined as the minimum size of infeasible set. For example, a K uniform matroid has a girth of K plus 1. As another example, let's take a look at graphical matroids. It's okay if you're not familiar with them. It's very simple. Given any undirected graph G, simply let the elements to be the edges and the feasible sets will then be the forest. For instance, in this graphical matroid, we have this green sets, for example, to be feasible sets because they contain no cycles. Meanwhile, this red set is infeasible because it contains multiple cycles. Going back to our result, we proved that for some graphical matroid with arbitrarily large girths, there is no profit inequality algorithm that gets better than the trivial competitive ratio of 1/2. Therefore, having large girths alone does not necessarily imply a good profit inequality. So, having this negative result, we turn to look at more restrictive conditions. And our second result is indeed a positive one for k-fold matroid unions. The k-fold matroid union F to the k is defined as follows, where a set S is feasible in F to the k if and only the set if the set can be partitioned into k feasible sets in the original matroid. And for example, for K uniform matroid, it is exactly the k-fold union of one uniform matroid. So this also generalizes the concept of K uniform matroid. As another example, consider the two-fold union of the graphical matroids we've just seen. In this two-fold union, the originally feasible sets remains feasible. And the blue set, which is originally infeasible, now also becomes feasible because it can now be partitioned into two feasible sets in the original matroid. However, this red set is still infeasible because it cannot be partitioned into two originally feasible sets. Going back to our result, we show that for any k-fold matroid union F to the k, there exists a 1 minus O of square root of log k over k competitive algorithm, which is tied up to logarithmic factor. Now, before diving into our result, let's first take a look at a simple algorithm for k-uniform matroids. Note that this algorithm is not the optimal one, but it's extremely simple. In this algorithm, we will call an item I to be active whenever its value is greater than some fixed threshold Ti. Note that this threshold is carefully chosen such that the expected number of active items will be at most k. After that, for each active item, we will first have a dropout phase where we might simply ignore the item with a small probability. And if an active item is not ignored, then we will accept it whenever there is remaining space. So basically, dropout plus greedy. I'm skipping a lot of details here, but I hope the overall framework of the algorithm is clear. And here, what we really care about is the probability of an active item being selected. And it turns out that if for every item I, every active item I, such probability is 1 minus epsilon, then together with carefully chosen thresholds, the competitive ratio of this algorithm will be 1 minus epsilon, which is very good. So to analyze this, in the dropout phase, we already know the probability of the item being ignored is small. Therefore, it suffices for us to bound the failure probability of the greedy process. And this task turns out to be fairly easy because after the dropout phase, the size of remaining set of elements will be smaller than k by a significant margin. Note that we name this quantity occupancy, as later we're going to generalize this concept to k-fold Matroid unions. Then, since the occupancy is simply a sum over independent Bernoulli random variables, we can use Chernoff bound, which gives us a strong concentration here. And this tail bound further implies that the probability of occupancy exceeding k is negligible, which means the greedy fails with negligible probability. As a result, the whole process will succeed with a high probability. And we're done here. Next, our plan will be to generalize this framework to k-fold Matroid union. And for that purpose, we will start from deriving a generalized occupancy measure, which intuitively means the number of slots occupied by a set S. And in the k-uniform Matroid case, this is simply the size of S because it's a uniform Matroid. However, for general k-fold Matroid unions, it turns out that we should really define this quantity with respect to specific elements. For instance, let's go back to this two-fold union of graphical Matroid. And let's take a look at the occupancy of this orange set with respect to different elements. With respect to the bottom edge, its occupancy should be 2, since both slots are occupied, and this edge cannot be further added to any of them. With respect to the right edge, however, its occupancy should be 1, because now this edge can be added to the second slot. So the orange set S only occupied the first slot for the right edge. And formally, we can show that for any k-fold Matroid unions, there exists occupancy function omega I for every element I, such that First, it maps every set S to an integer between 0 to k, indicating how many slots that the set S have occupied. And whenever the occupancy is smaller than k, it means that the item I is compatible with the set S, meaning it can be further added to any feasible subset of S, which matches our intuition. And importantly, this function is also monotone and one-Lipschitz, which allows us to later use our Bicriterion concentration inequality. And also, note that this function can be very general, and there's no hope for directly applying some Chernoff strength tailbound. Now we're ready to sketch our algorithm and the final analysis for k-fold matrix unions. The algorithm follows a similar structure, but we will first feed every element into a chain decomposition process, which is quite involved. And I'm not going into details, but trust me that after this, the occupancy of the remaining set S will be away from K by a significant margin, just like the K uniform matrix case. Then, by looking at the blue set S prime after another dropout phase, we can use our Bicriterion concentration to derive a nice tailbound of the occupancy of S prime based on the expected value of occupancy of S. And by simplifying it, we can conclude that the occupancy of S prime is smaller than K with high probability, which means the whole process will succeed with high probability. And that eventually will imply a 1 minus O of square root of log K over K competitive ratio for our algorithm. And that will be it. In conclusion, we have three main results in this work. The first result is a Chernoff strength Bicriterion concentration inequality. The second result says that large girths does not suffice for nearly optimal profit inequality. And the third result shows that k-fold matrix unions do suffice, which is proven using the Bicriterion concentration. For the last result, there are several specific open questions. The first one is whether this ratio can be further improved to 1 minus O of 1 over square root of k, which will then be as good as the k uniform matrix case. The second one is whether similar positive result can be shown for anything that is more general than k-fold matrix unions. And I believe that's all I have. Thank you.